Alrighty, so today we're going to be working on mini lab number 5, which is on RC circuits. So for those of you on Zoom, the file should be available under the mini lab section of our Moodle page. And I'm going to project it in just a second as well, so we can talk about the different things. If I can get all this junk out of my way. Let's see, Dropbox. All righty, so we are going to be using the Digilant board today, but instead of you guys having to learn how to use this old outdated piece of equipment, you'll just be relying on me to use it correctly, which should be pretty straightforward. So we can actually skip most of this first bit of material here. So blah, 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 let's go down here. So the first step is we're going to use a multimeter to measure our 1 kiloohm resistor. So I have a multimeter right here next to me. So let's take that data real quick. Pull one leg out. The other leg out. And so I am getting 985 ohms for my resistor value. I think that's the only time we're going to use the multimeter today. So get this guy plugged back in. So our resistor is 985 ohms. So now let's talk a bit about this experiment. We're asked to build the circuit below, which has already been done on the Explorer board, and it's asked to read the instructions. We're going to be using what's called an analog wave generator. So in our previous labs, everything that we've done has been based on DC circuits. Now we no longer have a DC circuit. So we're going to be replicating the switching operation that we've seen in our transient analysis circuits by using a square wave. So that means that we're going to have some voltage signal. So this is our baseline. This, where this is V as a function of time, and this axis is time. And then we are going to have it go high for some duration, low for some duration, et cetera, et cetera, et cetera. So at no point are we actually having 0 volts. It's switching back and forth between, I believe, positive 2 volts and negative 2 volts. So we're really going to be considering what we count as t is equal to 0 and what we count as t is equal to infinity in this case. So I will look at a graph in a moment, but effectively if we have the frequency right on our square wave, such that the duration of each interval is long enough for our signal to decay, every time we change state, we can treat that as a new t is equal to 0. It just depends on if we want to look at a charging cycle or a discharging cycle for our capacitor, which is what we'll talk about in just a moment. So we've done all of this kind of stuff. Now we need to actually look at our waveform. So I'm going to move some of this stuff out of my way. So I'm going to turn on my analog wave generator. I'm going to turn on my scope, and I'm seeing some stuff that does not look how it's supposed to look. And I can tell that because it looks like channel 2 is, let's see, so scope 1. So channel 1, my yellow thing, is supposed to be a square wave, and it's not quite a square wave. It's getting some clipping, and channel 2 is supposed to be my output, and that's not what it's looking like. So give me just 1 second to go back here and double check my circuit. Sorry, Davis said he had this set up, and apparently he was mistaken. Blah, blah, blah. All right, I'm just going to tear this stupid thing down. So from AWG1 to our resistor, one leg. Out to some point on our board. Then we have our capacitor, goes to our ground. We have scope 1 is going to be measuring input signal. And scope 2 is going to be measuring our output signal, which is the voltage drop across our capacitor. So let's look at this bad boy again. There we go. All right, let me share this with everybody. Share screen. All right, so hopefully everybody can see our waveforms now. So we have a yellow waveform, which is our square wave. There's a little bit of what's called Gibbs distortion in this area, which I'm not trying to move stuff around. But it's why we're not seeing a crisp corner there. But overall, it looks very, very close to a square wave. We can see that, let's see, where are we at? The minimum and maximum voltage for scope 1. So who can tell me what those are going to be based on this graph? Anybody? Can we see? I can see the scale on the graph, but can anybody else? Let's start there. So it should be pretty close to positive 2 volts for our maximum value and negative 2 volts for our minimum value. All right, I wish I could draw on this, but it won't let me. So if we look at my cursor here, everybody can see that little thing. The bottom line is at close to negative 2 volts, and the top line up here is right spot on at 2 volts. And that is actually the maximum value and the minimum value of our capacitor waveform as well, right? So our input signal is the yellow, which is purely a square wave. And then our output signal, which is the voltage drop over our capacitor, is that exponentially growing or exponentially decaying signal, depending on whether or not you're looking at it charging or discharging. So I'm going to slide this over so that we can see a full, effectively discharge cycle. So it's starting from positive 2 volts, exponentially decaying down to negative 2 volts, and then over the charge cycle, it's starting at negative 2 and exponentially increasing until we see it reach the positive 2 volts. So our answers, generally speaking, to this whole thing are going to depend, like our value for the time constant, which is what we're trying to calculate, is going to be the same regardless of whether we look at a charge or discharge cycle, but it is going to influence our equation for the response as to whether we're looking at charging or discharging. So which one do you guys want to look at? A charge cycle or a discharge cycle? Charge, okay. So here's a charge cycle right here in the middle of the screen. And if you look on your lab sheet, it says the voltage across the capacitor, which is oscilloscope channel 2, the blue curve, should have an exponential form fitting AE to the negative T over tau plus B. So I'm going to ask you guys a simple question. Does that equation look generally familiar? Good. So what does B represent in this equation then? Y at infinity, exactly right. So it's simply the value that the voltage settles to after it's stopped exponentially increasing. So we can look at this graph pretty easily and figure out what B is, right? What's it going to be? 2 volts, exactly right. What does the quantity A represent? Got them backwards. Y at 0 plus minus y at infinity. But yeah, so it's that first term, the coefficient of our exponential response. So t is equal to 0 plus in this case is, can I move this over slightly? Yeah. So I have it set up right now where effectively it looks like our capacitor is switching at a time of 0 milliseconds according to my scale, because I can, kind of slide things back and forth. So in this case right now, we're literally considering this to be our 0. This is when our switch arguably changed position, because it's when our input voltage changes state from -2 volts to +2 volts. So what's the value of the capacitor voltage at this time t is equal to 0? What's the value of the blue curve? -2. All righty. So if y at 0 plus is -2 and y at infinity is +2, then what's A? -4, right? -2 minus 2. So we should have -4 e to the minus t over tau plus 2 as our equation. Now, if we move down to the last bullet point on this page, it says that using the above calculated values for A and B, calculate the voltage at one time constant. So this goes back to our fundamental definition of what a time constant is. A time constant is when the value either increases or decreases by 36.87% of its initial value, which we can get simply by multiplying our coefficient A times e to the -1 power. Because that means that our time is exactly equal to tau, our time constant. So if we plug in our value for A, multiply it by e to the -1 power, and add B to it, what do we get? Give me a number. 0.5284, so 528.4 millivolts, okay? So whenever our voltage signal is increasing and has that particular value, that is exactly one time constant. Now I need to go through and find my cursors real quick. So I'm gonna have to slide this way. All righty. So I'm gonna move, if I can target it, there we go. I'm gonna move that cursor, t is equal to 0. I'm gonna slide this guy back over. All righty. And so what I'm looking for now, can you guys see where it says channel 1 and channel 2, and the voltages are kind of changing as I move my mouse to the left and the right? So what I'm looking for is for channel 2 to be exactly equal to 528.4 millivolts, or as close as I can get it. That's good enough for government work. Alrighty, so I've set my second cursor, and it's reading somewhere close to 530 millivolts. It's moving between, say, 529 and 531 just because there's thermal noise in the system. If we look down at the bottom, there's this thing that says X2 delta 1, 279.04 microseconds. That is the time difference between our two cursors. So if I have my voltage set, or excuse me, my cursor set to where my channel 2 voltage is roughly 530 millivolts, then that means that X2 delta 1 is a analytical measure of what our time constant is for this circuit. We know exactly what our value should be at the time constant, and so we figured that out, okay? So our time constant is then, like I said, 279.04 microseconds. So now it's time for you guys to do some math and figure out what value of C must we have. You guys on Zoom, feel free to chime in at any point. Anybody get a number? So we know tau, we know R. Okay, 2.832 times 10 to the negative 7. So I got it as 283.3 with some rounding in there, nanofarads, 10 to the minus 9, because I work in units of nanofarads, microfarads, etc. All right, so most of the lab is done. There's just one last little thing that is kind of a discussion type question. But yeah, this is the voltage drop over a capacitor. We are seeing that the inclusion of a capacitor into this system forces the response to have that exponential growth because the capacitor voltage cannot change abruptly. So we are seeing literally what the math described perfectly based on our simple derivation that we did in class about how the voltage drop and current over a capacitor related. All right, so the very last thing on the lab assignment says to change the frequency to 500 hertz. So let's do that real quick. Go to my wave generator. Now things look a bit different, right? So somebody describe to me what's going on here. Exactly right. We're not allowing the capacitor enough time to fully charge or discharge when we increase our frequency by a factor of 2.5. If we instead increase it to 1,000 hertz or 1 kilohertz, it would be even more pronounced, right? So could we use these higher frequencies to get a good estimation of what our time constant is? So that's a yes or no question. No, right? Because if we never allow it to settle, then we can't really see, we don't have a good estimation of what's going on at y is 0 minus and 0 plus, and we certainly don't have a good estimation as to what's going on at y at infinity. What can we do to change our time constant? Yeah, we'd have to change a resistor value or something like that. There's nothing fundamentally that we could do to this circuit other than literally changing the components by saying putting another resistor in parallel or another resistor in series or adding another capacitance or something like that. Okay, we got finished with that. A bit faster than I thought. David said it would take about 30 minutes and we did it in 20. So before we let you guys go, which if you want to just bail, that's fine. Does anybody have any questions about transient analysis that I could potentially answer? Since we do have a good 40 minutes before the next group of students is going to come in. Anybody got any questions about homework or anything, or what material is going to be on the test or stuff like that? Yes, sir. The next test is exactly 1 week from today. So Monday evening at 6, same room as last time. So 212 or 24 or something like that. I don't know. I'll figure it out, but it's the exact same place you took it last time. That's what's it. Yes, so it'll be pretty much the exact same format. I'll probably do the review on Zoom as well, just so that I can get everybody all in one class meeting. Let's see when I got a question in chat. How did we get the capacitor value? All right, Cade, if you know tau and you know R and you know what the time constant for a RC circuit is, tau is equal to R times C, you use algebra. So tau is equal to R times C tells us that C is equal to tau over R. So we had 279.04 microseconds divided by a resistor value of 985 ohms gives us a capacitor value of 283.3 nanofarads. All right. I use the measured resistor value. If you just use a 1 kilo ohm resistor, it's literally 279.04 divided by 1,000 is 279.04 nano. Yeah. Yeah, I use the 985 personally. So any other questions regarding, you know, any of this stuff? Or are you taking it easy today? All right, maybe next lab I'll have to prepare something so we don't get out so early. I thought this would take longer. Would have taken much longer if you guys did it. Oh well. Alrighty, so on the agenda for today is working a lab. And the lab today is dealing with RC circuits. So let me share this with everyone. All of you on Zoom, this document is available in the Moodle page, where if you click on mini labs, it should have mini lab number 5 and all that kind of stuff. And then also you can submit it in the online submission portal at the very bottom of the page. Alrighty, so let's see. We scroll through this guy. First thing we need to fill out is the resistor value in our circuit, which I have previously measured to be 985 ohms. So hopefully at this point, you guys don't need a demonstration of how to use a multimeter to measure a single resistance value. So we'll just put in 985 right there. And I've already got the circuit built. But let's talk about things real quick. The different components of this circuit. So obviously the resistor and the capacitor, that bit's fairly self-explanatory at this point. AWG1, that is what's known as an analog wave generator. So up to this point, everything that we've done in this class has been using DC sources. An analog wave generator is a voltage source that can provide square waves, triangular waves, and sinusoidal waves that may or may not include a DC offset. We are going to be dealing with a square wave today. So let's talk about what that is very briefly. So in a square wave, this is going to be our voltage signal as a function of time, and this axis will be our time axis. We should observe something like this. So at, let's just say t is equal to 0, it's some value, and then some time later, it switches down to a negative value, and then back up, and so forth, and so forth. So we can define one period of our square wave as the distance between the peaks when it's ascending, so when it switches to high, or we could alternatively say it's this guy down here, or we could look at the middle. It doesn't particularly matter how we measure the period, just that we acknowledge that it is a periodic function. Okay? So we have some maximum voltage V naught and some negative voltage, or minimum voltage negative V naught. So it's oscillating between a high value and a low, so let's say 5 volts, negative 5 volts, 5 volts, negative 5 volts, et cetera, et cetera, et cetera. So exactly half the time it's high, exactly half of the time it's low, and we're going to work under the assumption that the fall time and the rise time is very, very small, so that this doesn't look like trapezoidal. It looks very, very close to just a series of rectangular pulses. So the reason why we're going to be using a square wave in this particular case is because it's going to mimic a switching function, right? And so what I mean by that is that every time we see our voltage signal change from positive to negative or negative to positive, that's a new operation of effectively us opening or closing a switch, all right? So the key here is to use a frequency such that we allow the signal enough time to decay, right? Because if we look at our response, y of t is equal to y at 0 minus for t less than 0 minus, and y at 0 plus minus y at infinity, e to the minus t over tau, and running out of room here, so plus y at infinity for t greater than or equal to 0 plus. We're going to need to allow this transient condition time to actually decay out in order to apply our response equation to what we're going to physically see, right? And so I'll show you what that means actually in just a moment. So actually, let's do it now. Let's see, stop sharing that. Start sharing this. So this is our signal if we don't allow enough time. So this is our input signal is operating at a frequency of 1 kilohertz, which means it's cycling 1,000 times per second. The yellow curve is supposed to be our square wave of our input. So we can see that it has a peak value of +2 and a minimum value of -2. There is a little bit of distortion in as much as there's some curvature, but it's as close to a square wave as we're going to get out of this board. But we can see the blue curve there, that is our capacitor voltage, okay? So it's never reaching the maximum value of the input voltage nor the minimum value, and it's because we're not giving it enough time to fully charge or discharge. So if we play around with the frequency a little bit here, so let's say that we go to 500 hertz, so we're having our frequency. See, it's a little better, but we're still not actually achieving that peak positive value and peak negative value. So let's drop it down once more to 200 hertz. And we can see now, this is looking at just a charge cycle, that we're giving our capacitor enough time to reach its final value, and then probably a full another half a millisecond or so, which doesn't seem like a lot, but for the component values here, that's enough time for it to finally settle to a value at what we're going to call y at infinity, right? And if we looked at a discharge cycle, we can see that it also follows that it falls down, and then it's able to maintain that final value for roughly half a millisecond. So this is a graph that we can actually analyze to figure out what's going on with our circuit. Okay, so now that we've got that taken care of, if we go to, let's say, page 4, that's where we have the next things that we need to fill in. I've done all the other work, and we've gotten a 200 hertz, 4 volt peak-to-peak square wave. So first, let's talk about why this is a 4 volt peak-to-peak square wave, when it's obviously got a maximum value of +2 and a minimum value of -2. What does peak-to-peak mean? So we measure the maximum value and the minimum value, and the difference between those is the peak-to-peak value. So this is a 2 volt square wave, but it's a 4 volt peak-to-peak signal because its positive peak is +2 volts, its negative peak is -2 volts, and 2 minus -2 is 4. So I just wanted to be clear about that because we're going to be talking about operational amplifiers and doing a lab on them pretty soon. And the concept of peak-to-peak voltages will come up again there. So looking at this graph, I've said it just a moment ago, but what is the maximum value that we see on the yellow curve? So it's, if we look at the scale mark over here on the left-hand side, which you guys can't see my, for sure, that's weird. Okay, now you can. So you can see that the peak value is about 2, pretty much spot on. And the negative, the most negative value is right on at -2, right? So Vmax is +2 and Vmin is -2. If we further look at this sheet, it says the voltage across the capacitor, which is oscilloscope channel 2, the blue curve, should have an exponential form fitting the equation A e to the -t over tau plus b. Now, hopefully that equation form is pretty familiar to you all. Because I just wrote it down a minute ago, effectively. But what does the term B represent in that equation in your lab sheet? Oh, you guys didn't get the lab sheet. Yeah, that's why you're not looking at them. That is my fault. I feel like a complete and utter moron, so give me just a moment to pass these around. So turn to the, I think it's the 4th page. That's where we're at this point. Thank you. Right smack in the middle of the page now, so you guys can actually see it, because I bothered to give it to you, is an equation. So I will repeat my question now. What does that B represent? That's exactly right. Whatever the function is at infinity. So in this case, that would mean that it's going to be whatever value the capacitor voltage settles to, which brings us to an important distinction here then. Are we going to look at a charge cycle or a discharge cycle for our capacitor? We're going to get the exact same value for our time constant. It's just going to change our equation slightly because we're going to have a different value of t is equal to 0. So pick one is effectively what I'm saying. Do we want to look at At charging or at discharging? All right, so charging. So let's slide this guy over. So this is a full charge cycle of our capacitor, starting from where this leftmost red line, which is what I'm using to indicate effectively T is equal to 0. When our input voltage changes states, which means it's the beginning of our transient condition as our capacitor tries to catch up, okay? So for this charge cycle, based on our graph, what is B? What value does the capacitor voltage settle to? 2 volts, right? What does the quantity A represent? So A, 0 minus is at, or recall that that's at DC steady state. So 0 minus is really representative of everything to the left of the red line, or at least for a little bit of time, because we have a square wave, so it's constantly oscillating. So it'll be 0 plus minus what's going on at infinity, right? Because we have a total response situation here. We're adding the switch in. If we only did 0 plus, we would find that our equation would be discontinuous, and we know that can't be true for a capacitor voltage. Okay? So A represents y at 0 plus minus y at infinity. So y at 0 plus is what the value of the capacitor voltage is immediately after that leftmost red line. So what's that? And when I say immediately after, I mean literally a fraction of a second after. What value does the blue curve have at this point in time? I'm trying to, -2, okay? So -2 minus y at infinity, which Ms. Pereira said was +2, gives us what for A? Right, -2 minus 2 is -4. So A is -4. Based on our graph, B is +2. So our next step is asking us to calculate the voltage at exactly 1 time constant, okay? So at 1 time constant, the ratio of T over tau should be what? Right, because at 1 time constant, if T is equal to tau, then tau over tau is 1, right? So what we're going to do is we're going to take A, which was -4 volts, multiply it by a factor of e to the -1, and then add to that B, which was +2 volts, in order to determine what value our capacitor voltage should have at exactly 1 time constant. So take a moment to perform that calculation for me, please, and then tell me what the answer is. 0.528 volts, okay? So roughly 530 or so millivolts. The reason why I say that's because that's what I was able to actually slide my scale over to. So what I've done here, I put my leftmost marker at T is equal to 0, and I'm moving this right-hand marker to a point where, if you can see, channel 1, the voltage doesn't really change as I move over, and it's because it's the top of that square wave. It shouldn't be changing a whole heck of a lot. Channel 2 is the instantaneous value of my capacitor voltage. So as I slide this guy over to the left, I'm going to try. So somewhere between 525 and 529. So that's probably pretty close to my value of 528. I can see down here at the bottom, it says X2 delta 1 is 278.06 microseconds. So that is the time difference between my 2 markers. One is set at T is equal to 0, and the other one is set at exactly 1 time constant later, which means the time constant for this RC circuit is 278.06 microseconds. So if you go to the last page, where it asks what the time constant is, well, we just figured that out. I'm going to ask you guys to calculate what value the capacitor must have, given that R has a measured value of 985 ohms, and our time constant has a measured value of 278.06 microseconds. Where do we get tau? So it's the time difference between these two red lines, which is given by this quantity here that says x2 delta 1 is 278.06 microseconds. It's a capacitor circuit. Although that is a good question that I might ask in a moment. What's the equivalent inductor value that would give you the same time constant? Anybody got a number for me yet? So this is an RC circuit, which means tau is literally equal to R times C. And since you know, pardon? What units? Pardon? So the units on our time are in microseconds, and the units on our resistance. Okay. .823 times 10 to the negative 6. Okay. That means it's 283 roughly nanofarads is our capacitor value. 283 times 10 to the minus 1. Wait, shouldn't be 278 divided by less than 1,000. Maybe that's right. Let's see. Oh yeah, no, that's exactly 283.3. Yep, 283.3 nanofarads. Now, because Eric over there asked a very good question, whether or not we had a capacitor or inductor, what would the equivalent inductance, what inductance would we need to put in to get this exact same time constant? Right? So if we know tau is equal to L over R, that means our inductor value would simply be tau multiplied by R, right? So 278.06 times 10 to the minus 6 multiplied by positive 985 would give us a 273.8 millihenry inductor. All right, so this honestly didn't take as much time as I thought it would, probably because we didn't have to troubleshoot anything, which would have taken up most of the time you guys are doing this. So let's see. So there's an exam 1 week from today. Hopefully you guys are all aware of that. If not, you are now. The material on that exam covers from Thevenin and Norton equivalent circuits, which were lectures 9 and 10, up through what we did today. Really, so finishing up transient analysis. So we're going to cover op-amp circuits on Wednesday and Friday of this week, and that material will not be on exam 2. So with that in mind of what's on exam 2, do any of you guys have any questions about any homeworks or in-class assignments or anything? Or do you want to just get out 30 minutes early? I can put them up today. If you send me an email to remind me to do it. My last name at lawtech.edu. 2 N's. Any other questions, comments, etc.? All right, so op-amp circuits are what's coming up next, as I mentioned. They are an interesting component in as much as they're an integrated circuit in and of itself. We're not going to be looking at them as a circuit because a very basic op-amp contains tens of resistors and transistors, a couple of capacitors and all that kind of stuff, and it has 7 pins. So we're going to be looking at it from a component level because the behavior of an op-amp is very, very well defined under some specific conditions that we'll talk about in class. Yeah, there is a lecture video right now. It's available on op-amps. It's about 10 minutes long, and it's the hottest of garbage. So I'm going to be re-recording it to make it more informative and less crap I threw up on the internet because I had to get something on there this evening. So I would not watch that video unless you want to see how bad it is until tomorrow. It's been up there forever because I haven't had a chance to change it. Yeah, I don't remember when I recorded it, but I remember I did it in a real big hurry, and it's very, very bad. So I'm going to make it hopefully significantly more informative in the future. Okay, so unless anybody has anything else, I guess we're done for the day. So we already did that at the very beginning, actually, but sure. So the very last question, it asks us to change the frequency to 500 hertz and 1 kilohertz and look at the output changes, and then why would these high frequencies be a bad idea. So if I bring my frequency back up to 1 kilohertz, or 500 hertz for that matter, we can't use this frequency to determine the time constant because we're never allowing our capacitor to fully charge or fully discharge, which means we never really know what's happening at t is equal to infinity because we never got there. Does that make sense? Exactly right. It's never getting a chance to settle to some final value. And that's a large part of what defines the response equation, right? No, it's charging and it's discharging, but it's never reaching a finite fixed value. So like if I hooked up a capacitor, higher frequency means more cycles per second. So, okay, actually, I don't even need to do this. All right, so for the frequency of 1,000 kilohertz, what is the period, right? So time and period are inversely related. So T, capital T, let's go back to sharing this. Let's go back to this here graph, okay? So capital T, period, is 1 over f, our linear frequency. So if f is 1 kilohertz or 1,000 cycles per second, what is the time of 1 period for our square wave that we have? Do the math, figure it out. Simple. Just putting it in your calculator, actually, since we know what f is. 1,000 hertz. 1 over 1,000 is what? So it should be 1 millisecond. Okay. So 1 millisecond is our period. And that means that for 1/2 of a millisecond, or 500 microseconds, it is at positive 2 volts. And for the next 500 microseconds, it's at negative 2 volts. Okay? So the fundamental definition of the time constant is how long it takes to decay to where it decays from one value to e to the -1 times that value. That's one time constant. So it's a reduction in signal strength by, I think, 37%. In 2 time constants, it decays down to around 13%. And 3 time constants is around 6%. And 5 time constants is what an engineer considers to be infinity. So it's decayed to less than 1% of its original value. So we say that it's close enough to its final value. Well, at a frequency of 1 kilohertz or 1,000 hertz, 1,000 cycles per second, our signal is switching in under 2 time constants. So we're nowhere close to the 5 time constants we need for it to settle. Okay, so that's why it's a terrible idea to measure our time constant based on a signal that never ever settles. We don't have any real reference point, right? Our capacitor voltage, like, we know how it's behaving at t is equal to 0 minus and t is equal to 0 plus, because it can't change abruptly. But if we were looking at, say, the capacitor current or something like that, even that measurement would be questionable because we don't have that fundamental relationship. And we definitely can't say that at t is equal to infinity, it has some value, because it's never settled. So this graph does not give us the required information to determine the total response of our capacitor voltage. And it's purely because the frequency is too high. Alrighty, any other questions? All right, see you guys on Wednesday. Turn in your things up here, please.